All right, so there's a handout today because I want to make sure you have all those definitions and theorems in front of you. You've already watched the video, so we don't have to watch the video in class. That's good. So a scalar field is a function whose input is coordinates in space and the output is a scalar. A scalar is just a number, in contrast with a vector, which is a list of numbers. A vector field is a function whose input is coordinates in space and the output is a vector. So you have 2D vector fields and 3D vector fields. If I say that a vector field is conservative, I mean that this vector field has an associated scalar field that we call the potential field. And if you were to take the gradient of the potential field, remember potential is a scalar, and I take the gradient of that scalar field, it's going to give me a vector field. That would be a conservative vector field. So you really can't separate these two definitions. Because every conservative vector field has a potential field, potential function. And every potential function, every scalar field in general has a associated corresponding conservative vector field that you get if you take the gradient of any scalar field. So we'll do a few examples of those. If I have a 2D scalar field, then we say that, sorry, I don't know what I said. If I have a 2D vector field, that vector field is conservative if and only if the curl is 0. And another way to say that is that the partial of the first entry with respect to the second variable is equal to the partial of the second entry with respect to the first variable. If that happens, then the way we define curl for a two-dimensional vector field would be 0. I'll show you that later. We'll actually derive that. Curl is calculated using this formula where you take the gradient operator and do a cross product with the vector field. Where whenever I say the gradient operator, I'm talking about a vector where each entry is like a partial derivative operator. And so whenever I say take the cross product, what I mean is like match up the entries as you would by taking a cross product, but then you're not really multiplying, are you? You're not saying I'm multiplying the partial with respect to x times some other expression. You would be taking the partial with respect to x of the expression. And so it's kind of a, I'm trying to think of like an MNU appropriate word for it. Because the only word that's coming to mind is to say, as what I've read in several old textbooks, is like, this is a bastardization of the notation, right? Like I'm not actually multiplying, but I didn't know if that would be a word on the Nazarene do not say list. If the curl is 0, it's irrotational. 3D vector field is conservative if and only if it's irrotational. So if and only if the curl is 0, it makes it conservative. The divergence of a vector field is a scalar that is calculated using the formula this. And once again, this is not really meaning that we are going to multiply some partial derivative operators times some expressions. It means we're going to take the partials and then we're going to add them up. I'll show you what that means with some examples. And then if the divergence is 0, we say the field is divergence free. And this is kind of a funny theorem, but if you've got continuous second partial derivatives, so that means like the entries in your vector field are kind of analytic looking normal functions that we're used to, then we'll find that the divergence of the curl of f is 0. So this is just a quick summary of today that you can take home and you can put it on your fridge with a little magnet. You can remember it for the rest of your days. The divergence of a vector field at a point in space is a scalar that quantifies how much nearby vectors point away. So you saw this in the video. I'm glad everybody watched it. But if I'm concerned about this point P, the divergence is telling me, okay, in the neighborhood of this point, how much are these vectors pointing away? And this would be a picture of positive divergence. And of course, negative divergence is what it would look like if I have some point I'm interested in, and in the neighborhood around that point, all the vectors are pointing in towards the point. That would be negative divergence. But again, I can't animate this for you. That's why I wanted you to watch the video so bad, is so that you can see this animated. It's really helpful. So the curl is telling me, if I've got a point in space, how much are the vectors kind of pointing in a circle? How much are they swirling around? This is clockwise, so it would be negative curl. And if it were moving counterclockwise, we'd be talking about positive curl. And of course, this is like a three-dimensional phenomenon. So what you actually get when you take this cross product, remember, the cross product gives you a vector, not just a scalar. In 2 dimensions, the analog of curl is more like a scalar. And so in 2 dimensions, we'll talk about that. But in 3 dimensions, curl is a vector. And so the vector that you calculate when you do the curl is going to be pointing in the direction of the axis of rotation, right? So in like 3D space, things have to rotate about an axis like this. And so the curl vector is going to point in that direction, to where if you were looking down the vector, you see it counterclockwise. So divergence is a scalar, curl is a vector. The cross product is specifically defined for 3D vectors. And what I mean by that is, like, if I've got u cross v, remember this? You have to write uv minus uv, uv minus uv, uv minus uv. And then you write 2, 3, 1. And then you write 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. This is defined for 3-dimensional vectors. What if I want to do this with 2-dimensional vectors? Like A is just the vector A1, A2, and B is just the vector B1, B2. Well, we pretend that they're 3-dimensional vectors that are still living in the xy plane, so the z component is 0. And then whenever we do this cross product, the first 2 entries are going to be 0. Because in the first 2 entries, do you see how there's always a third component invoked here? But the third components are zeros. And it's only the third entry of the cross product where we don't have any third component. And so whenever I write the cross product of 2-dimensional vectors, it's really just a scalar. So we could define the cross product of 2 2-dimensional vectors just to be this scalar. Okay? And with that said, curl, the definition of curl for a vector field is defined as the gradient operator cross product with the vector field. Well, if I have a 2-dimensional vector field, this is going to be the partial of the first, no, sorry, second, I guess, because the gradient operator is the A and the vector field is the F, so this would be actually the partial of the second entry with respect to the first variable minus the partial of the first entry with respect to the second variable. And notice that this is a scalar then. If I've got a two-dimensional vector field, then the curl of that is really just a scalar. I think that's even something that's mentioned in the video, although it's been at least a year since I watched that video. I think he does say that, like, okay, what you're looking at in the video is just the stuff happening in 2 dimensions, so he's talking about curl as being a scalar. But in 3 dimensions, curl is a 3-dimensional vector because of the whole cross product business. Okay, let's do some exercises. Given the following vector field, find a formula for the divergence of F. So, we say divergence of F. That is the, quote, dot product between the gradient operator and F. And so, here's my gradient operator. Dot product with my vector field F, 2xy plus z, x squared plus z squared plus 1, 2yz plus x. And what you're doing is not actually multiplying, but we're just going to take the partial with respect to x of 2xy plus z. So what is that? 2y. Okay? And then we're going to take the partial with respect to y of x squared plus z squared plus 1, which is 0. And then we're going to take the partial with respect to z of 2yz plus x. What's that? 2y. So the divergence of F is just 4y. Questions? No? All right. Given the following vector field F, find a formula for the curl. Curl is the hard one. Divergence is nice and easy, but curl takes a little bit of thinking here because we're talking about that gradient operator cross product F, and my gradient operator is the partial with respect to x, the partial with respect to y, the partial with respect to z, cross product with 2xy plus c, x squared plus z squared plus 1, and 2yz plus x. And I can never remember the cross product formula, so I have to go and write that down too. All right, uv minus uv, uv minus uv, uv minus uv. 2, 3, 1, 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. Okay, so finally going to write down what this cross product looks like. Is going to be the partial with respect to y of the third entry in F, right? Because 2, 3, so the partial with respect to y of 2yz plus x. What's that partial? 2z. All right, and then minus the u3 v2, so the partial with respect to z of x squared plus z squared plus 1. What is that? 2z. Okay, next, u3 v1, so the partial with respect to z of 2xy plus z. 1. Minus u1 v3, so it's the partial with respect to x of 2yz plus x. 1. And then u1 v2, so the partial with respect to x of x squared plus z squared plus 1. 2x. Minus u2 v1, so the partial with respect to y of 2xy plus z. 2x. So this time the curl is coincidentally the 0 vector. And since this is the 0 vector, we say f is irrotational. What else do we know about f? It's conservative. Yeah, if my curl ends up being the 0 vector, and it's not always the 0 vector, right? But if it happens coincidentally to be the 0 vector, then we say f is irrotational, and that means f is a conservative vector field. Any questions about that one? No? All right. Given the following vector field f, determine whether the vector field is conservative. We actually already did that. If it is, find the potential field of f. So what we know about the potential field is such that if I take the gradient of the potential field, I will get this vector field. That's what it means as a definition to be the potential field, is that if I take the gradient of the potential field, I get the conservative vector field we're talking about. This is the same vector field from before, so we know it's conservative. And well, what does that mean? The potential field is a scalar field. And that means the partial of f with respect to x is going to be equal to 2xy plus z. And that means the partial of lowercase f with respect to y is going to be x squared plus z squared plus 1. And that means the partial of lowercase f with respect to z is going to be 2yz plus x. That's what it means when I say the gradient of lowercase f is equal to the vector field f, capital F. So what we're going to do is 3 things. we're going to take the antiderivative of 2xy plus z with respect to x. We're also going to take the antiderivative of x squared plus z squared plus 1 with respect to y. And then we're also going to take the antiderivative of 2yz plus x with respect to z. Because if this is the derivative with respect to x, I should be able to take the antiderivative and get back to f. And same thing with the other two, right? So what's the antiderivative of 2xy plus z with respect to x? Plus and then what's the antiderivative of x squared plus z squared plus 1 with respect to y? And what's the antiderivative of 2yz plus x with respect to z? So here, these are all supposed to be lowercase f, my scalar field. All of these expressions over here in orange are supposed to be lowercase f, my scalar field. And you notice they don't match exactly. They have some similarities, like x squared y shows up in these two, and xz shows up in these two, and yz squared shows up in these two. But they're not exactly the same. Really, the trick to understanding this is this little constant. When we were just doing single variable calculus, this constant was just a real number, right? It couldn't be anything that included your variable. But this time, since I'm taking the antiderivative with respect to x, this little guy is only constant with respect to x, but it could include y and z. And this little guy only has to be constant with respect to y, but he could include x and z. And this little guy only has to be a constant with respect to z, but it could include x and y. And so now under this kind of inspection, we say, all right, x squared y plus xz plus some terms that could include just y and z but no x's. And so terms like that might be like yz squared plus y. Do you see what I'm saying? And this one, is saying, all right, my antiderivative is x squared y plus yz squared plus y plus, and this could just include x and z only. So like x times z. That would fit here as part of that constant. And then this is, of course, yz squared plus xz plus this little c is only talking about terms that include x and y only. So that would be like x squared y would actually belong right here. And so once you look at all three pieces of your puzzle and you start to kind of match it up, then you can reconstruct your scalar field. So altogether, my scalar field is going to be x squared y plus, I'm going to underline the stuff I've already used, xz plus yz squared plus y plus c. And you don't have to do this, but if you wanted to check your work, oops. You don't have to do this, but if you want to check your work, what you could do is take the partial derivative of f with respect to x and hope you get back the first entry, and then take the partial derivative of f with respect to y and hope you get back the second entry, and then take the partial derivative of f with respect to z and you hope you get back the third entry in your vector field. But do you see the relationship between the lowercase f potential field and the capital F vector field? Got it? Okay. All right, given the following vector field f, calculate the divergence of the curl of f. If you've really been paying attention, you probably know what the answer is going to be. But let's pretend we don't already know the answer. And so we'll start off by taking the curl of f. And the curl it's going to be a 3D vector. And it's going to involve some partials. It's going to be the partial with respect to y of 1 plus y plus x. One minus the partial with respect to z of y squared minus z squared. Negative 2z. So two negatives makes a positive, and that's my first entry. The second entry in the curl is going to be the partial with respect to z of z minus xy. Does it help if I write the cross product formula? It's going to help me if I write the cross product formula, so I'm just going to write it. So it's 2, 3, 3, 2, 3, 1, 1, 3, 1, 2, 2, 1. And of course the curl is the cross product. So the curl is going to be the partial with respect to y of f3 minus the partial with respect to z of f2. Then it's going to be the partial with respect to z of f1 minus the partial with respect to x of f3. And then the partial with respect to x of f2 minus the partial with respect to y of f1. Okay. So back to it. 1 minus the partial with respect to x of f3, which is 1, and then the partial with respect to x of f2, which is 0, and then minus the partial with respect to y of f1, which is negative x. So altogether, my curl is 1 plus 2z, 0x. And we are ready to calculate the divergence of the curl of f, which is going to be the partial with respect to x of 1 plus 2z, which is 0, and the partial with respect to y of 0, which is 0, and the partial with respect to z of x, which is 0. So sure enough, the divergence of the curl of f is 0.
Also, I have a strange question.
Mm-hmm.
Do you think we can get points for our quiz today?
I thought there was going to be a quiz. I didn't say it was going to be a graded quiz.
Oh my goodness.
You're silly.
I gave you guys a test. I didn't say it would be graded.
I just
It's gonna be a final. It's not gonna be graded.
You just remember that for the
And I'll
final.
keep that quiz.
Yeah.
I didn't have time to type up a test, or a quiz, I mean. I don't have time to type up a quiz.
Exactly.
Yeah. And me and Aaron got the questions right,
To just put 100 in. How much do you want to count for? 99% of your...
Yes, that'd be nice.
Yeah, like a 10 points?
Yeah, 10 points. That could make or break my.
We'll see.
Yeah, me and Aaron got 100 on it. Everybody got 100.
If you do, you to go. If you do, I won't talk to you the rest of class.
Okay, if f is a vector field with continuous second partial derivatives, then the divergence of the curl of f is 0. So let's try it out. The curl of f, and I think I wrote this down while I was working on the previous problem, is over here. This is my curl of f. So without plugging in anything specific, now if I take the divergence of the curl of f, remembering what the divergence means, right? If I've got the divergence, that's going to be the dot product between my gradient operator and g. So that's going to be the partial with respect to x of g1 plus the partial with respect to y of g2 plus the partial with respect to z of g3. Now, the divergence means I'm going to take the partial derivative with respect to x of the partial with respect to y of f3 minus the partial with respect to z of f2 plus the partial with respect to y of the partial with respect to z of f1 minus the partial with respect to x of f3 plus the partial with respect to z of the third entry in the curl, which is the partial with respect to x of f2 minus the partial with respect to y of f1. So I'm going to write this down again, and I'm going to switch my notation over from Leibniz notation to Lagrange notation for partial derivatives, because it's faster for me to write it that way. When I distribute the partial with respect to x, derivative additivity and everything means I can write this f3 where I take the partial with respect to x and y, minus this f2 where I take the partial with respect to z and x. Sorry, with respect to y and x, and then z and x, plus this f1 where I take the partial with respect to z and y, minus this f3 where I take the partial with respect to x and y, plus this f2 where I take the partial with respect to x and z, minus this f1 where I take the partial with respect to y and z. If my second partial derivatives are all continuous, that means it doesn't matter what order I take derivatives in. In fact, it wouldn't matter if I took the partial with respect to z and then x, or the partial with respect to x and then z. As long as all of my second partial derivatives are continuous, then the order in which I take partial derivatives does not matter. And so now when I've expanded everything out, and you think about that, then you can see why these highlighted terms are going to cancel. When everything cancels out, the divergence of the curl of f is going to be 0.
What did that mean for it to be continuous again? Like, what was that idea of continuous?
Continuous?
Yeah.
That means there's no discontinuities. So, I mean, it's a good question. I like your question. Continuous means a function, and we're going to think about first the function of one variable, like f of x, is continuous at a point C if the limit exists and the limit is equal to the value of the function there. And if your function is continuous at every point in a real interval, then we say the function is continuous along the interval. And for a multivariable function, what it means to be continuous is that you are continuous in all three variables, right? That there's no discontinuities, there's no poles, there's no, essential discontinuities, there's no, I don't know, what's another kind of discontinuity? Step discontinuities. Learned about all those stuff back in Cal 1. But this applies to like most things, not all things, but as long as your function doesn't shoot up to infinity or have a place where it's undefined, then it's continuous. So that was the proof that the divergence of the curl of any vector field is 0 as long as it has continuous second partial derivatives, which is like not a big assumption. It's a pretty reasonable assumption. The last thing we want to talk about is that a 3D vector field is conservative if and only if it is irrotational. Because the irrotational bit makes it really easy to tell whether or not a field is conservative. This is saying the curl of f is 0. And that's easy. It's easy to calculate the curl of a vector field. And if we find that it's 0, we know the vector field is conservative, and that's great because that means it has a potential field. But what we need to show is, like, what's the connection here? Why would having 0 curl implicate that there is a potential field that generated this conservative vector field? So if and only if means we need to prove 2 directions here. Like if and only if means like it's conservative if it's irrotational, meaning irrotational implies conservative. And then the other direction is saying I need to show that conservative implies that it is irrotational. So first, let's show that conservative implies irrotational. And to do this, we're going to start off with a scalar field, f, I have this bad habit in this chapter. When we get to these lessons, I always just say f, even though we were dealing with a capital F and a lowercase f. So lowercase f is a scalar field. And then we're going to define capital F to be the gradient of lowercase f. So capital F is going to be a vector field where I have all of the partial derivatives of lowercase f. And that means the way I've constructed the capital F is conservative. And now we just have to prove that this is irrotational. So let's take the curl of f. Man, I cannot remember that curl formula. It's tough. I'm gonna have to like reproduce it from scratch every single time. But here's the curl. I'm taking the partial with respect to y of f3 minus the partial with respect to z of f2. So here's the partial with respect to y of f3, which is the partial of lowercase f with respect to z, minus the partial with respect to z of the partial of lowercase f with respect to y. Then the second entry in the curl, I'm going to have to scroll up to show you, is right here. It's the partial of f1 with respect to z minus the partial of f3 with respect to x. So the partial with respect to z of the partial of lowercase f with respect to x minus the partial with respect to x of the partial of lowercase f with respect to z. And then the last is going to be the partial with respect to x of the partial of lowercase f with respect to y minus the partial with respect to y of the partial of lowercase f with respect to x. Yuck. And it may look really confusing still, but it's not. It's getting better. what helps is the Lagrange notation. I could have written this fzy minus fyz. Second entry fxz minus fzx. And then last entry fyx minus fxy. So the curl is 0, and it's irrotational. So we completed the first step. We showed that conservative vector fields always have to be irrotational, because the definition of a conservative vector field is we start with the scalar field and then we take the gradient of that scalar field, and then when you take the curl of the gradient of the scalar field, it turns out to be 0 every time. And I guess the underlying assumption here is that your scalar field has continuous second derivatives. The other side of this, the other side of the coin, is show that a field being irrotational, meaning that the curl is equal to 0, implies that it must be a conservative vector field.